All right, this is a fun little example to think about, get our mind going again on this relativity idea in terms of length contraction. And I just think this one is super fun. Let's take a look at it. A very fast train with a proper length of 5 meters. So there's that word, proper length. Pop it in your head what you think that means. Is passing through a tunnel that's 200 meters long, according to the measurement of the people on the grounds. Remember, as we moved into relativity, we had to think about where our measurement was being taken. So the tunnel is 200 meters long according to the people on the ground. The train has a proper length of 500 meters. Think about what that means. The train speed is such that, as observed on the ground, it entirely fits inside the tunnel. That means for an observer on the ground, the front of the train is just emerging from the end of the tunnel as the back of the train is just disappearing into the tunnel, so that the length of that tunnel is exactly equal to the length of the train. How fast is the train going in order for that to be the case? And how would an observer on the train describe what they see as they pass through this tunnel? Is the emergence of the front simultaneous with the disappearance of the back of that train? So are they simultaneous, like the observer on the ground would say they are? Okay, so we're going to look at this. I just think it's so fun to think about. All right, how do we tackle this problem? Well, it has to do with length contraction, right? And we want to think about, all right, what is my proper length? We're told that, but why is that the proper length? We're taking a measurement of the train, which means to get a proper length, that is in reference of the train itself, as if the train was in rest at that reference point. And so the person on the train would say that the length of the train is 500 meters. They are at rest relative to the train. The train is the object that we're measuring. It needs to be at rest relative to the observer in the same reference frame, okay? So L naught is equal to 500 meters. And again, somebody on that train is going to say that's the length of that train as it's moving. All right, so an observer off the train, all right, so now I'm an observer on Earth, they are our length, which we know is related to L naught times the square root of 1 minus v squared over c squared. This length L is 200 meters. The bridge is measured at 200 meters. Sorry, the tunnel. The tunnel is measured at 200 meters by an observer on the ground. The tunnel is on the ground. The observer is on the ground. The tunnel's proper length is equal to 200 meters. The observer is on the ground, not on the train. This is the length that the tunnel and train appear to them because the proper length of the tunnel is 200 meters. That is their reference frame of length. And if the train entirely fits inside of it, they think the train, they see the train is a better way to say that, as 200 meters. So now we just solve for V. So we have 200 equals 500 times the square root of 1 minus v squared over c squared. And when we solve for v, in that relationship, we get that v is equal to 0.92 times the speed of light. So 92% of the speed of light that train is traveling. All right. So kind of fun way to think about things. Now I have a question. How does a passenger on the train see it going through the tunnel? How does a passenger on a train? So what would the passenger, I put that into the words. Sorry about that. I'll move that down. What does the passenger on the train see? Well, a 500-meter train cannot fit in a 200-meter tunnel, right? And so from the perspective of the passenger on the train, the train will not fit inside that tunnel. The front end of the train will be emerged before the back end of the train comes in. The tunnel is not going to fit the train. And in fact, the tunnel is moving. The tunnel is even moving faster in the perspective of the person on the train. From the perspective of the person on the train, the tunnel is moving. The tunnel is moving. It has proper length 200. If I calculated the length the person in the tunnel sees, the length the person on the train sees the tunnel, if I calculate the length the person on the train sees the tunnel, it's contracted. Then there's no way it's going to fit. We already know it's not going to fit by the tunnel proper length. And so the person on the train does not see the train inside the tunnel. They see the event of the front of the train and the back of the train not happening, entering the tunnel, or emerging and entering, as not simultaneous. So the person on the track sees it as simultaneous. The person on the train does not see it as simultaneous. Wah! Mind blown. It's that whole idea that simultaneity is not absolute. It depends on the reference frame. So fun to think about. All right, good job.